Welcome to Calculus. Today we will investigate the extreme value theorem, and we'll look specifically to find absolute extrema of rational and radical functions on a closed interval. We'll take a look at one example. Our example here is the function y equals -4 over x squared plus 1. So when we think about that function, that's definitely a rational function. And we're interested in what is this function doing on the interval from -1 to +3. X equals -1 all the way over to x equals 3. And our goal again is to find what's any points that are absolute minima. What are any points that are absolute maxima for this function on that interval? Well, let's remember first of all what the extreme value theorem says. So the extreme value theorem, it makes a claim about how many maxima or minima we could expect for a function on a closed interval. So extreme value theorem, we'll go ahead and state it. So if a function f of x is continuous on an interval from a to b, so that's our hypothesis. The main requirement there is that the function be continuous. Then the function f of x has at least one absolute maxima and at least one absolute minima. And we just have to keep in mind this could have the maxima or the minima within the interval. It could be one of the endpoints. I forgot the word maxima. And at least one absolute minima in the interval from a to b. And so for our function, really just what we need to check is the function continuous from -1 to +3? And then we just need to look, where is our absolute minima? Where is our absolute maximum? Or do I have multiple of each? Well, let's start off by graphing this function. I just want to see what the function looks like on this specific interval. So let's set up a table. And I'm just going to graph exactly what this interval is describing from -1, 0, 1, 2, all the way to +3. So I just want that window of the graph. And then let's calculate these outputs. So I've got -4 over x squared, so -1 squared plus 1. So that's going to give me -4 over -1 squared is 1 plus 1 is 2. And then that would divide -4 divided by 2 to -2. At 0, that's -4 over 0 squared plus 1, which is going to reduce to -4 over 1, or just -4. And here at +1, I'm expecting something like what we saw for the output of -1. Let's see if it changes at all. So +1 squared plus 1 in denominator, that's -4 over 2. So we do have a duplication here between -1 and 1's output. It's both -2. All right, now at +2, -4 over 2 squared plus 1 is going to be -4 over 5, or -0.8. And lastly, at 3 here, -4 over 3 squared plus 1. And that's going to give me -4 over 3 squared is 9. 9 plus 1 is going to give me 10. That's going to reduce down to -2 over 5, which is -0.4. So that gives me enough to graph this function on that window. So we'll just plot this one. -1, -2 is there in quadrant 3. 0, -4 is right on the y-axis between quadrants 3 and 4. 1, -2's in quadrant 4. Everything else is going to be in quadrant 4. So 2, -0.8, and then 3, -0.4. So a little less than half. So if I were to graph this one, it is continuous, so it does fulfill that hypothesis part of the extreme value theorem. And so for this question, we can really see really clearly where is our absolute minimum, where is our absolute maximum. It appears that we have one of each. So just to identify where they are, this lowest point here at 0, -4, I could identify that as my absolute minimum. And remember, the theorem says we have at least one. We could have more than one absolute minimum, but that's the absolutely the lowest point. There's no other point on that red curve that has a y value lower than -4. Similarly, for the maximum, this end point on the right, so that's going to be at 3, and as we calculated at -0.4, that is the absolutely highest point on the graph. That's our absolute maximum. So we were able to do quite a lot just from graphing the function, but we do want to confirm what we've seen here by taking the derivative of the function and setting it equal to 0 and then solving. So remember, the strategy for finding a critical point by taking the derivative of a function is really saying where is the slope of the tangent line to this function equal to 0. And recall, anytime we have a tangent line that has a slope of 0, it's horizontal. So that means that the graph at that point is either reaching a maximum or a minimum value. The idea is if the function looks like that, the tangent line when the slope equals 0 should correspond in this case to an absolute max. And it would work very similarly. I could do another part of this function if it was like a sine curve. Slope equals 0 could also indicate an absolute minimum. So let's use that strategy just to confirm what we think we are seeing, that specifically that the minimums here at 0, -4. So I just want to take the derivative of the function, so y prime, and it's set up as a quotient, so I'll use the quotient rule. Let's set up our function by distributing that negative to the 4. So -4, that's my f of x over x squared plus 1, that's my g of x. So I'm going to use the quotient rule here. So it starts off g of x, so that's x squared plus 1, the original denominator, times the derivative of f. Well, that's just a constant. Derivative of -4 is 0. Minus f of x, which is -4, times the derivative of g of x. G of x, x squared plus 1, so that's going to be 2x. And that's all over g of x, x squared plus 1 squared. So again, I'm just interested in where does this derivative equal 0. So this first term in the numerator will cancel out, and what we'll have for the second term is going to be a positive, double negative there would be a positive 8x over x squared plus 1 squared. So that really reduces quite a bit. And when we consider where that value of the derivative equals 0, really what we're interested in is this numerator. The denominator would tell us where is the function undefined. We're not really interested in that. We're interested in where does it equal 0. So I'm just going to take that numerator, 8x, set it equal to 0, and then solve. So I would divide there by 8, and I'd see that the value of the function should have a slope of 0 at the x value of 0. And when I go back to my table, that checks out. This x value of 0 is giving the absolute minimum value of -4. So although we can do a lot of this work on a graph, we also can follow up or initially find that absolute minimum or maximum by taking the derivative and setting equal to 0 and solving the equation that results. Thank you for joining for this investigation of the extreme value theorem. We'll give you a chance to practice your own location of absolute minima and maxima. See you soon.